Good morning, all of you. I am Dr. P.S. Kaushik, Principal at Sri Digambar Institute of Technology, Dosa, Rajasthan. I will be taking this subject, Engineering Mechanics, and this today is lecture number 27. Here we will be dealing with the analysis of moment of inertia. In this lecture, we will be dealing with the perpendicular axis form, parallel axis form, and radius of gyration with some simple problems. First of all, let us recollect what we learned in the last lecture. Mass moment of inertia, Im, it is the inertia against the turning moment, torque. It is similar to the inertia against the force to resist change in state in case of rectilinear motion. Area moment of inertia, it is the resistance to bending moment of a beam. It is 2. It is the second moment of mass and second moment of area. Its unit is meter to the power 4 or kg meter square. Perpendicular axis form. The moment of inertia of a plane area about an axis normal to the plane is equal to the sum of moment of inertia about any two mutually perpendicular axes lying in the same plane and passing through the given axis. Okay. Now let us concentrate here. This is some area. These are its centroidal axes x and y. Then any axis which is perpendicular to this plane, and passing through the point of cross section of these two axes and which is perpendicular to the plane, that is like this top type, then we call it that z axis. Then in that case Iz equal to Ix plus Iy. This is called the perpendicular axis form. In the next slide we will be dealing it with some more details. Okay. Perpendicular axis form. Here, concentrate here. This is the one axis, this is the other axis, and will be the axis perpendicular to the plane of paper. You can say, concentrate like this. Consider in your classroom that horizontal two axes at the floor, Ix and Iy, and the axis in the corner you can find which is just going upward in the corner, then we will call it z axis. So three dimensional you can understand like this. Here Iz equal to Ix plus Iy. Refer to the figure area. Concentrate at the small area dA. Then you can find by the method of Pythagoras theorem triangle, this triangle, right angle triangle, you can say r square equal to x square plus y square, and multiply it by total area, that is integration dA. Then it becomes r square integration dA equal to x square integration dA plus y square integration dA. Then this is will be called as, by first principle you can say this is Iz, this is Iy, and this is Ix. So you can say Iz equal to Ix plus Iy. This Iz is also called polar moment of inertia. That will be explaining in the next slide. What do we mean by the polar moment of inertia? Sorry. Polar moment of inertia. First of all, you should understand what is pole. Pole. You can say electric pole, and when you concentrate, you will find that electric pole is having cross section very small, around. If you say electric pole made of RCC, at the base it is around 1 feet in length, thickness, width, and around 6 inch in thickness. 1 feet in width and 6 inch in thickness. And as you are going on the top, then its width is decreasing. At the top it is around same, width and thickness are almost same. So you can concentrate that it is having a length of around 18 feet, whereas the dimensions are 1 feet by half feet, and we call it pole. So you can say any member whose dimensions, whose length is much larger than its cross section, we call it pole. And moment inertia along the length of the structure we will be calling that polar moment of inertia. So refer to this figure. This is the cross section area of this small cross section area, and this much is its length. So we call it the pole, and the moment inertia about z axis we will be calling it polar moment of inertia. Apply the parallel axis theorem here. You will find Jo equal to Ix plus Iy, or Jo you can say it is Jp, polar moment, sorry, Ip. Ip means polar moment of inertia. I think it is clear now. Go to the next slide. Parallel axis theorem. Consider again this small area and concentrate on this area. This area is dA. By very first principle, I is equal to y square dA. This is the then Ia, moment inertia about this axis, is y square dA, since its total dimension is y here. Divide it y dash plus a whole square dA, then it becomes that, and open this, the equal to y dash square dA, integration y square dA plus 2d y dash dA plus b plus d square into dA. Consider this portion. This is the moment of this is, you can consider this. This is the y dash and integration dA. It means moment of area about its centroidal axis, and the moment of area about its centroidal axis of a plane is always 0, because there is no arm. Y dash is almost 0 there. So this dimension becomes automatically 0. Ix, this is Ix, this is d square integration dA. So you can say Ia equal to Ix plus a d square integration dA. What is d square? D square is the distance between the centroidal axis and the axis under consideration. So parallel axis theorem says that the moment of inertia about an axis which is parallel to the centroidal axis will be equal to the moment of inertia about the centroidal axis plus square of the distance between the two axes and the multiply by the area of the plane under consideration. Similarly, it can be applied for mass also. Okay. So Ia equal to Ix plus d square integration dA. Again, the next slide. Radius of gyration. What is radius of gyration? Radius of gyration is the radius of gyration of an area. Radius of gyration or gyradius of a body about an axis of rotation is defined as the radial distance to a point which would have a moment of inertia the same as the body's actual distribution of mass, if the total mass of the body were concentrated at that point or length. Radius of gyration is a measure of distribution of mass about the given axis. If the particles of body are distributed around the axis of reference, then moment of inertia is less. And if the particles of the body are distributed away from the axis of reference, then moment of inertia will be very high. The knowledge of mass or area moment of area and radius of gyration of the body about a given axis gives the value of its moment of inertia about the same axis, even if we do not know the actual shape of the body. I will be explaining in details on the next slide. Consider this area, the A with moment of inertia I x dash. Imagine that the area is concentrated into a strip parallel to the x axis with the equivalent, which is equivalent I x dash. Then I x is equal to k x square into A, or k x is equal to I x upon A. Concentrate here again. Just concentrate this area into a strip, and it should be placed at such a distance that its moment of inertia does not alter or remains same. The distance between this reference axis and this strip will be called that radius of gyration about that axis. Again, take another case, this one. This is the y-axis. At the moment of inertia about this axis was Iy, and you reduce this area to a strip here, which is ky away from the y-axis. If this ky should be such that the moment of inertia of this area when concentrated into a strip remains same, because you know that area, the distance from the reference axis is squared when you are reducing the moment of inertia. So it should be such that when you are reducing the area, the k should be increased, the distance should be increased such that the moment of inertia about this axis remains same. Then the distance ky will be called radius of gyration about y-axis from the strip of the area. Here its importance, as discussed in the earlier slide, is that if we know its radius of gyration and we know its mass and area without knowing its shape, then we can find out very easily what is its moment of inertia about that axis or about that reference line. Similarly, the case is for in this circular lamina, that polar moment of inertia becomes, the polar radius of gyration comes out to be this. And from the principle of symmetry, you can find Ix equal to Iy, and from the perpendicular axis theorem we know Iz equal to Ix plus Iy, or Iz equal to 2Ix, or you can say this relation holds. Then moment of inertia of an area by integration. Method of integration we will be applying here. You can say that for the figure under consideration, this is dx, this is dy, then dA becomes dx into dy. Then Ix equal to y square dA, dix equal to y square dA, and dy Iy equal to x square dA by very first principles. Then Ix is equal to integration y square dA, and Iy equal to integration x square dA. The evaluation of integrals is simplified by choosing dA to be a thin strip parallel to the one of the coordinate axis. That this we will come to know in the next slide. Now let us find out the moment of inertia of this rectangular strip about its base B, that is axis x, and this is axis y. This is axis x, this is axis y. These are the two centroidal axes, capital X and capital XX and capital YY. Okay. Here apply the first formula, the method of integration, IB equal to integration y square dA, considering the small strip of thickness dy and width b. The area becomes b into dy. Then IB equal to integration y square dA, on applying the limit 0 to h, it becomes bh cube by 3. Similarly, to find the moment of inertia about centroidal axis capital XX. Here same formula, the only limits are reduced from minus b by 2 to minus h by 2 to h by 2. Y square dA, you can say again, this is the strip under consideration, this distance is, say again y, this is dy, then just concentrate it from plus side to negative side and integrate it. When moving from plus side to negative side, the integration becomes minus h by 2 to h by 2 y square dA, and on integration you will find this relation. This is a simple relation. Similarly, the case can be for about this axis and about this axis. Same steps, same way, when you proceed, then it becomes diy equal to x square dA, which we x square s dx. On integration you will find this. For when we are about this, and for this it will be again 1 by 3 I small y 1/3 into hb cube. One point to remember always is that you have to make a cube of the dimension which is perpendicular to the axis of reference. Always you should remember this. sorry, battery was low, so this disturbance was expected. Now you can apply the parallel axis theorem also. I b equal to Ix plus this is h by 2 square A. So bh cube by 12 plus h by 2 whole square bh, which comes to bh cube by 3. Problem 1. Determine the moment of inertia of triangle with respect to its base B. A differential strip parallel to the x-axis is chosen for dA. dIx is equal to y square dA, or d and dA equal to L into dy. This length is L chosen here. For now you can say that when y is changing, then the value of L is also changing. So we will be having one equation only, so it can solve only for one variable. So applying the principle of similar triangles, we have to reduce one dimension into another with the help of the standard dimensions. So by similar triangle you can say L by B equal to h minus y upon h, or L equal to B into h minus y upon h. So we have reduced this L in terms of y with the help of the constant B and h. So dA becomes B into h minus y upon h into dy, like this. Now on integration, integrating dix from y equal to 0 to y equal to h, we will find this relation bh cube by 12. Problem 2. Determine the centroidal polar moment of inertia of a circular area by direct integration. Using the results of part A, determine the moment of inertia of the circular area with respect to the diameter. Solution: an annular differential area element is chosen. This is the area we have chosen, small. dZp or dJo equal to u square dA, and dA equal to 2 pi u du. This is the strip. You can say that du is the thickness, and length, this peripheral length is 2 pi u. So total area becomes 2 pi u into du. Then on Zp equal to Zo, the dJo, integration dJo 0 to r u square, just put up the values, u square 2 pi u du, 2 pi is taken out, and this will be integration 0 to r u cube du. On integration you will find that this is 2 pi u to the power 4 by 4, 0 to r, then u will be replaced by r simply. So z, then it becomes your z equal to pi r to the power 4 by 2. From symmetry you can say Ix is equal to Iy, this was simply. So z equal to Ix plus Iy, or 2Ix. So you can say that Ix equal to Iy equal to diametral moment of inertia is pi r to the power by 4, or pi by 64 d to the power 4 in terms of diameter. Now it comes to be parallel axis theorem. Moment of inertia to be found for about this axis. This is t axis, here is taken here. The moment of inertia it of a circular area with respect to tangent to the circle. Then again apply the principle of that is parallel axis theorem. IT equal to I bar plus A dq. D is the distance between the centroidal axis and the tangent axis. With D is equal to the distance, no diameter, which is equal to half the diameter, that is R, radius. So apply this formula here, pi over 4 r to the power 4 plus pi r square into this r square. On mathematical calculation, it comes out to pi r to the 5 pi r to the power 4 divided by 4. This is the one. Similarly, the moment of inertia of triangle with respect to the centroidal axis. Just we know about base, it was pi b h cube by 12. When we apply the about this centroidal axis I b dash, then a dash minus a square, a d square. D is the distance between the centroidal axis and the base axis, a axis. So bh cube by 12 minus half bh is the area into 1/3 into h square, because we know that this is the h by 3 distance from the base. Then it comes out to be bh cube by 36. Centroid of any triangular dimension is 1/3 from the base always. These are some standard figures, and the moment of inertia with respect to the dimensions shown in the figure. About the base, for a rectangular section, it is bh cube by 3, and about the centroidal axis, it is bh cube by 12. And for ZC, that is any axis which is perpendicular to the plane, it will be 1 by 12 bh into b square plus h square. Just add these two. These two, you will find this relation. For triangular section, about the base, it is bh cube by 12, and about the central point, it is bh cube by 36. Similarly, for a lamina of circular section, Ix and plus and Iy equal to pi r to the power by 4, and for the polar axis, it is half of these two. This is double of these two, that is pi by 2 pi r to the power 4, or pi, you can, in the terms of diameters, you can say Ix equal to Iy equal to pi by 64 d to the power 4, and Iz equal to pi by 32 d to the power 4. Again, these are dimensions for other, this is half lamina, circular lamina, quarter circular lamina, and ellipse. You can concentrate here and find out. These will be used when we will driving the analysis of composite areas and masses in the next slides. Thanks for watching this lecture. References are Engineering Mechanics by D.S. Kumar, Engineering Mechanics by R.S. Kurmi, and Google search engine. Sorry for the interruptions in between, because there was an interruption because of the battery got low, and I have to connect it with the charger. Thanks for watching this video.